again, I'm going to look at the absolute value of this. And I'm going to look at this over here. Whoops. The sum n equals 2 off to infinity of 1 over, you're going to get n times the natural log of n squared. Now looking at it, let's be careful about this. It's going to be a continuous positive and a decreasing. I'm going to use the integral test on it. And let's write that down. So I'm going to do the integral test on this, and I'm going to start at 2, go off to infinity, and you're going to get 1. I'm going to simplify the log. I'm going to say 1/2, because the 2 comes down, and you get x ln x dx. All right. I'm going to do the integration on the side work. I'm going to put this over here. I'm going to let u equal, let's see, ln x, and du would be 1 over x dx. So I see this guy looks like, let's see, 1 over u du. Let's make sure I did that right. Yeah, it looks good. And that's going to be the natural log, the absolute value of u. All right, plus some constant c. What's u? U was, let's see, ln x, right? Plus c. So I think I'm ready to write this down. It's going to be 1/2 limit as a goes towards infinity. And then it's going to be, let's see, the natural log of the absolute value of ln x, let's see, evaluated from 2 to a. And get rid of some of my scratch work over here. Don't really need it anymore. Unless, of course, I'm wrong. If I'm wrong, I'm not going to need that anyway. So it's going to be 1/2 limit a goes to infinity. And let's write this down. So it's going to be natural log of the absolute value of the natural log of a minus ln, the absolute value, ln 2. All right, let's see if we can do that limit. And what would that give me as a goes to infinity? Well, unfortunately, it's infinity. All right, so I know this thing is not absolutely convergent. I know that much. All right, so what I want to do is I want to go back and look at it and do the AST on it. All right, so let me do the AST on it, alternating series test. AST. Let's put 1 down first, and I'll write down AN for you. AN is 1 over n, and that's going to be ln n squared. All right, so the first thing I'm going to show is that 1 n plus 1 ln n plus 1 squared is less than or equal to an, and that's n ln n squared. And by the way, the n's are going to be greater or equal to 2. Makes it a lot easier for me. So let's write that down, and you would get n ln n squared less than or equal to n plus 1 over, I'm sorry, not over, but ln n plus 1 squared. I can continue to rewrite that, by the way. You get n ln n. The 2 comes down, but I'm going to divide both sides by 2. You know, I got a lot of stuff written here, don't I? I'm going to get rid of these things. I'm done with the absolute convergence, by the way. I'm not going to, I'll just get rid of all that stuff over there. I don't need that anymore. I'm just doing the AST now. Seems conditionally convergent. All right? So let's write that down. Again, the 2 comes down, divide both sides by 2. You get n plus 1 ln n plus 1. All right? So, looking at it, I hope you're convinced at this point that this is true for n greater than or equal to 2. So I got that part covered. The next thing I'll do is just a limit as n goes to infinity. By the way, that's what I need to check, of an, which is 1 over n, ln n squared is 0. I'm going to convince that too. So there's two things I need to show. One, and that's the second thing. So I'm going to say it's conditionally convergent. Conditionally convergent. And that's it. Thank you.